Welcome. Today, we're diving deep into system design. We're not just talking about building an application, we're talking about architecting something that can grow from your first user to millions, maybe even billions, without collapsing under the pressure.
All right, so here's our game plan. We're going to start with the single most important decision you have to make in any distributed system. From there, we'll build up our architecture piece by piece. We'll cover scaling, caching, databases, and then we'll wrap it all up with a blueprint you can use for your own designs.
Before you write a single line of code or spin up a single server, you're faced with a choice. It's this fundamental trade-off that's going to define how your entire system behaves under stress. And it's a choice you simply can't avoid. And that choice is governed by the CAP Theorem. It's kind of famous, and for good reason. It says you can have three things: consistency, meaning everyone sees the same data at the same time; availability, meaning the system is always responsive; and partition tolerance, meaning it keeps working even if parts of the network fail. The catch? You can only pick two. And since network failures are pretty much a guarantee in the real world, your actual choice is always between consistency and availability. This right here is the perfect real-world example. Think about a banking system. It has to be consistent. Your bank balance can't be one thing in one place and something else in another. So it will choose to go offline rather than risk showing you the wrong number. It chooses consistency over availability. Now, a social media feed, it's the opposite. It prioritizes being available. You'd much rather see a post from a few seconds ago than see an error page, right?
All right, moving on. Let's say our app is a success, which is great, but our one lonely server is starting to smoke. This is a good problem to have for sure, but we need to solve it. It's time to think about scaling. So you're getting slammed with traffic. Your site is getting slow, maybe even crashing. What's the move? Well, you've really got two main paths you can go down to handle all this new attention. Okay, so option one is to scale up. This is called vertical scaling. You basically just buy a bigger, badder server. More CPU, more RAM. It's simple, but you'll eventually hit a maximum size. And it's a single point of failure. If that one machine goes down, you're offline. The other option, and this is how all the big services operate, is to scale out. This is horizontal scaling. Instead of one big server, we add lots of smaller ones. This gives us almost unlimited room to grow and makes our system highly available. Now, if you've got a whole fleet of servers, you need some way to manage the traffic, right? You need a traffic cop. And that's exactly what a load balancer is. It sits out in front and directs all the incoming requests to your different servers. One of the most common ways to do this is with an algorithm called round robin. It's super simple. As you can see, it just sends the first request to server A, the second to server B, the third to C, and then loops back to A. It just cycles through them. Another popular one is called least connections. That one's a little smarter. It sends the next request to whichever server is the least busy at that moment. Okay, but not all load balancers are the same. A layer 4 load balancer is a speed demon. It just looks at basic network information like the IP address and port. It's like a mail sorter, just reading the address on the envelope. A layer 7 load balancer, on the other hand, is much smarter. It can actually look inside the request, at the URL, at the headers. It's like the mail sorter opening the envelope to see what's inside. This lets you make much smarter decisions, like sending all requests for video content to a special set of servers. So, we've solved our traffic problem, but now we've got a new bottleneck. Every single one of those requests is hitting our database, and it's starting to slow everything down. What's the quickest way to fix this? Caching. The strategy you'll see most often is called cache ACID, and it works like this. Your application first asks the cache for some data. If the data isn't there, that's called a cache miss. So the application then has to go to the database, grab the data, and this is the important part. It puts that data into the cache on its way back. That way, the next time anyone asks for that same data, it's right there in the cache, and the response is incredibly fast. Now, there are other ways to do it. Write-through caching writes to both the cache and the database at the same time, which is safer. But there's another strategy called write-back. With write-back, you only write to the super fast cache and then immediately tell the user, we're done. The cache promises to write the data to the database later. The performance is amazing, but Think of it like a scratch pad. It's fast, but if the power goes out and you lose that scratch pad before the notes are copied to your permanent notebook, that information is just gone. Okay, caching made our reads a lot faster. But now we've another problem. Our database itself is just getting too big to fit on a single machine. The sheer volume of data is becoming the issue, especially for write operations. So it's time to scale the data layer. The answer is a technique called Database Sharding. Instead of trying to buy a bigger and bigger server, we split our data across multiple servers. Each piece is called a shard. We can do this based on something like a user ID, or just split the rows horizontally. The main challenge, though, is something called resharding. That's the really tricky process you have to go through when you need to add more shards and redistribute all the data. Now, here's a detail that can make or break your performance. How you generate IDs matters a lot. If you use standard UUIDs, they're basically random. That means every time you write new data, it could land on any one of your database shards. It's chaotic. But if you use something like a snowflake ID, which is time sortable, all your new data is sequential. This means your new writes are all happening in an orderly way, probably on the same shard, which is way, way more efficient. And of course, the kind of database you pick in the first place is a huge decision. A classic SQL database is what you want when you need rigid structure and absolutely guaranteed transactions, what we call ACID compliance. Think of financial systems. NoSQL databases, on the other hand, are designed for flexibility in scaling out horizontally. They're perfect for big data or for apps where the data model might change a lot. At this point, our system has a lot of moving parts. We've got a user service, a payment service, a notification service, all talking to each other. But if one of them fails, it could cause a chain reaction, a domino effect that takes everything down. We need to make these services more resilient and independent. A fantastic tool for this is a message queue. Here's the idea. Instead of Service A calling Service B directly, Service A just drops a message into a queue. Later, Service B, the consumer, picks up that message and processes it. This decouples them. If Service B is down for a few minutes, the messages just wait safely in the queue. Tools like RabbitMQ are great for this kind of work, while something like Kafka is built for handling massive streams of data. It's a total game changer for system reliability. And what about how these internal services talk to each other? For a public API, you'd probably use standard HTTP REST. But for the high-speed chatter between services inside your own network, you can use something much more efficient, like gRPC. It uses a super efficient binary format that makes it way faster and less resource-intensive than REST. It's really built for that internal, high-performance communication. Wow, we've covered a ton of ground here. Load balancers, caching, sharded databases, message queues. So let's put it all together. Let's create a repeatable process, a blueprint, that you can use to design any large-scale system. Here it is. This is a solid process. You always start by clarifying requirements, not just what the system does, but also how fast and reliable it needs to be. Then, you do some quick math to estimate your scale. Then, you can start designing your APIs and your database schema. Once you have that, you draw out the high-level architecture. And finally, you zoom in on the specific pieces and figure out where the bottlenecks are going to be. And really, that's what this is all about. System design isn't about finding the one perfect answer, because it doesn't exist. It's about knowing all the different building blocks, understanding the pros and cons of each one, and then making intelligent, deliberate trade-offs to solve your specific problem.